All right, here's our first lesson from chapter 2. We're just spending on one day talking over the basics of polynomials and how to find zeros and factors of polynomials. Okay, polynomials, just to quickly breeze through some of their characteristics. Okay, an expression with x that has real coefficients and whole number exponents. Each component is called a term. All right, each polynomial is a sum of several terms. The degree is the largest exponent, and the leading coefficient is that number in front of x with the largest exponent. We call that the leading term. Okay? Those are the basic characteristics of polynomials. All right? And for the most part, you'll know them when you've seen them. And in fact, so far this year, we have just studied polynomials because lines and quadratics are technically first and second degree polynomials. Lines are first degree polynomials. Quadratics are second degree polynomials. And we're just going to extend this topic to include third, fourth, and fifth degree polynomials. So we got to make sure we know a polynomial when we see one. Okay, for example, in part A, is this a polynomial? The answer is yes, it is. Okay, it has 4 terms. Okay, each one of those coefficients with the variable x raised to whatever power, those are terms. Okay, here the leading term on part A is 8x to the 5th, even though it doesn't come first, which it probably should. It has the highest power, which is to the 5th, meaning that's the leading term. That means 8 is the leading coefficient, and the degree of that polynomial is 5. Okay? Leading term is 8x to the 5th, leading coefficient of 8. That is a degree 5. Okay? In part B, the answer is no, that's not a polynomial. We get some goofy stuff going on by putting x over x plus 3. And the reason we don't consider that a polynomial is as we continue this unit, you'll see that functions that are considered polynomials have common characteristics in their graphs. And when we have this kind of thing going on with the x over x plus 3, that's actually just a ratio of 2 polynomials. It doesn't quite hold the same characteristics. Okay, that's what's going on there. Oh, here's just some of the types. Okay, and again, we've studied this. Already mentioned this briefly that we've really looked at those first 3: constant functions, linear, quadratics. We are really extending the discussion this unit to third, fourth, and fifth degree. Okay, and again, that degree represents the power, the highest power that a variable is raised to. Cubic, it's 3. Quartic, it's 4. Quintic is 5. Okay, and that's where we'll stop. In theory, polynomials don't stop at degree 5. They can continue going. We'll stop at 5. And really that's because modeling questions that involve, real life context, there's certainly a time and a place for higher degree polynomials past 5. They're pretty specific. They're usually higher end type of questions in applied science. More common real life contexts. Third, fourth, fifth degree, that'll really cover any applications we want to look at. We can evaluate with polynomials, okay? Just like any other function. If we wanted to evaluate h of 3, we take 2 times 3 squared plus 5. Let's see, that would end up being 23. We could certainly, if we wanted to, and at times a problem may call for it, we can substitute a complex number. And as you'll see in this example, oftentimes when we substitute a complex number, we can get a real number as an answer. Okay? 2 squared is 4. I squared is, well, I squared. But remember here that I squared is negative 1. This 4 should have remained a 2. Excuse me. Okay, so because I squared is negative 1, we'd have negative 8 plus 5, negative 3. Okay? We could substitute an expression with a variable in it, like 3p. Understand that if that happens in a problem, we would expect to have a variable in our answer. This would be 2 times 9p squared plus 5, which we could simplify all the way to 18p squared plus 5. That would be fully simplified. Notice I still have the p variable in my answer because the expression that I substituted in when I evaluated was 3p. We could also substitute an expression like p plus 2. For example, we could have 2 times p plus 2 squared plus 5. Okay? That would really involve a bunch of foiling. This would end up being p squared plus 4p plus 4 plus 5. When I distribute the 2, I'll get 2p squared plus 8p plus 8. Combining those like terms at the end for a fully simplified answer of 2p squared plus 8p plus 13. Okay? So that's just regular old substitution, otherwise known as evaluating a function. I want to take a second to show you a slick little method called synthetic substitution. Okay? As polynomials get longer, they can be kind of a pain to check, like to evaluate. You're seeing that those last couple that I was just doing, I was evaluating variables, so there was a little bit of simplifying to do. But look here, I have a cubic polynomial, and I want to evaluate negative 2, which looks like it could be kind of a hassle. There's a slick little technique that we will get lots of practice with, and we will continue to do it more in Learning Objective 2, known as synthetic division or synthetic substitution. Either name would be appropriate. I'm going to show you this one example on how to do it. Okay. I'm just dealing with the coefficients, and that's actually what makes synthetic substitution kind of handy, because I don't have to deal with any of the x's or the exponents. But here's how it works. I start by bringing down this 3, which I started with because that was the coefficient in front of x to the third. Bring down the 3, and then I multiply it by negative 2, and I get negative 6, which is what I put there. Negative 7 plus negative 6 is negative 13. Okay, so I add those two. And then again, I'll take the negative 13 and multiply it by negative 2. And I get 26. Okay? 2 plus 26 is 28. Times negative 2 is negative 56. And I get negative 53. And I'm kind of out of space. Okay? What this means is that if I were to plug negative 2 into this polynomial, I would get a y value of negative 53. Okay, and as you get good at synthetic substitution, you can start to do it really fast. And with just, I mean, when you get good at it, you could almost do it just as fast as you could plug those numbers into a calculator. And you'll actually see for higher degree polynomials, it's probably the quickest way to evaluate. Okay, really nice little technique. We'll practice it a lot more. Okay, if you want a little more practice, try that second one. The only thing I'll say there is notice that when you set this up, I'm not going to take the time to work through this one start to finish, but 5 on the outside, it would be 4, -3, 0, 7, and -2. The 0 is coming from the fact that there's no x squared term. I shouldn't skip over it, but the coefficient for x squared would be 0, which is why I put 0x squared. Take a look here. If -3 is a 0 of f of x, there I have a 4th degree polynomial, and I want to know what coefficient would I have to put in front of x squared to make that polynomial have a 0 of -3. Just remember here that when we say that -3 is a 0, I'm saying that if I put that in for x, it gives me a y value of 0. So if I set f of x equal to 0 and then put -3 in for x, the only variable or unknown piece of information that leaves me with is a, and I could work through that. Okay, and it's actually not as bad as you think. I think this first term simplifies to 162. This middle term becomes 9a. We still have the -6. It becomes, after we apply the exponents, it becomes a linear equation and isn't horrible to solve. But I could work that through and solve for a. Last thing, just one final note here that when you're dealing with polynomials and we want to find their zeros, factoring or using the quadratic formula, okay, is a common technique here. I got this quadratic right here. And this is just kind of a review of some of the work we've done with quadratics. This is factorable. -2 times -3 equals 6, and those add up to -5. Okay, and remember my goal of getting it split up into factors is I can set each individual one equal to 0. Okay, and find those zeros. Okay, so factoring will come back a little bit. Also recognize cases like the second one where it's already been factored. One factor is x to the third. Another is x minus 6. Don't make it more work. If you have a polynomial that's already been factored, and at any point you have to find the zeros, well, that's nice. Always just take those factors that you find. Again, that's really the purpose of finding them, is take each of those factors, set them equal to 0, and solve. All right? That's all we're going to cover for now, which was actually quite a bit for this first learning objective of Chapter 2. All right, feel free to work through some of those problems. I didn't work all the way through, and if you have questions on those, let's talk more.